Okay, so thank you guys for watching. So what we've done is we've already figured out how to get set up with MOBA Xterm and how to log into HPCC and get Cadence up and running. So now that we've gotten Cadence up and running, what we're actually going to do is we're actually going to do kind of just a very basic Cadence project. So what we're going to be doing is we're going to be looking at schematics and how to simulate those schematics in Cadence. Okay, we're not going to be touching on any of the layout yet. That'll come in the future. But what we are going to be doing is we're going to be figuring out how we can actually simulate some designs to make sure that we're getting everything up and running correctly and make sure that, excuse me, make sure that Cadence is actually working with us well. Because if you don't follow these directions, Cadence isn't exactly intuitive to figure out. So it's pretty important to have someone at least show you how to get through the beginning. So right now you can see that I've already logged out of the CPU because I wanted to start from the beginning. So this would be like I just logged into the Quanta server. So actually what I can do is I can just go ahead and Control D, that'll log me out of this. I can close this window. And then the last time, since we have it bookmarked, all we have to do is double click over here. It'll, in this case, it doesn't have to ask for my username because I told it beforehand. And I can just type in my E-Rater password and it'll let me into Quanta. Now, the first thing that we want to do is we want to make sure that we have a CPU allocated for us. That way we can actually get the high performance in the high performance computing center. The way that we do that is interactive-p Quanta. And then it should say it's granting us the job allocation, and then it's going to tell us the CPUs are ready for the job. So now we've got CPUs allocated toward us. Now we also need to module load Cadence. Now we can tell that we're interested in Cadence for this one, and it can load up all those Cadence commands that we need. Now if we ls and see where we're at currently, we're just in our home folder, and we do not want our Cadence stuff in this home folder. So what we'll do is we'll actually cd change directory into our Cadence folder. So wherever we're going to be running Cadence, we want to make sure that we're running it in that folder. And now that we're in this folder, we can simply run virtuoso and. And remember this and? That and is just there to make sure that we can still access the command line whenever we are running Cadence, okay? Because Cadence will stop our command line if we don't have this and we're not going to be able to do anything until we close Cadence, which isn't exactly good. So virtuoso and it will load up Cadence. It is a little bit of a job, so it might take a couple of seconds. And you should be greeted with this window, the CIW window. There may be a second window that pops up right here, but we'll talk about that here in a second. So this is going to be the very basic start of Cadence. Now, you might not have this library manager window here. So you can see this one's called the library manager. So you may not have this one here. Now mine, whenever I hit X, it doesn't exactly get rid of it. It just minimizes it. But what we can do is that we can actually, if we are just on this screen, we don't have that library manager screen, all we have to do is we just need to hit Tools, Library Manager. And then it will pop it up. Now, like I said, I've already got mine open, so mine opens up right here. But if you don't have a library manager window open, that's how you can get it up and running. Now, this window here, the CIW window, is actually pretty important. So this is where it's going to be talking a lot to us. So for example, whenever I was installing Cadence on a new server with a different PDK and everything, this actually gives quite a bit of information for how things are loaded. So it sees we can have a little bit of warnings, but we actually don't have to do anything about this right now. I've gone through and made sure that everything is working for our purposes. But if you do get some errors, maybe something isn't working, check out this window because it might give you a little bit more information than just staring at a red X. So if we start off from here, we're going to again use Tools, Library Manager, and pull up this Library Manager window. And you can see that from all the stuff that Dr. Lee has given us, it's actually loaded up quite a bit of stuff. So all of these NCSU libraries, these are all of the technology libraries that we're going to be using for this class. So all this stuff is developed, it's pretty intuitive and actually pretty easy to work with. So it might look like it's a lot, but really it's a lot easier compared to some other ones. It's a little bit more intuitive. So we can see that we've got a lot of different libraries here, but we don't want to mess with any of these, right? Because some of these are given to us directly from Cadence, some of these are from the NCSU group, and we don't want to mess with their stuff, right? So if I go in here and start messing with their stuff, I could cause some really bad things to happen. So we want to actually make our own library. So pretty much for every project that you're going to do, it's going to start off as a library. So the general structure, again, is library, cell, and view. Library is going to be the collection of cells, and cells could be anything from an op-amp, a digital analog converter, all sorts of things, okay? And then the view is going to be things like the symbol, the schematic, the layout, and things like that. So for this first project, what we're going to be doing is we're going to be making a new library. So the way that we make a new library is we hit File, New, and then we're going to make a new library. So we're going to click on that, and it's going to ask us for a little bit of information here. Now, this is going to be asking us where we want to store it, so I'm going to go ahead and store it in my AC_cadence folder. And up here at the top, I want to give it a library name. So you want to try and be descriptive, but since this is going to be the EDA number 1, I'm going to call this AC_EDA1. And that's about as descriptive as I need. So then we can hit OK. It'll start generating a new library. Now it's also going to ask us for a technology file. So what we're going to do is we're actually going to attach it to an existing technology library, because we're going to be using the NCSU AMI 06 or the 06 process. So we're going to attach it to an existing technology library. Press OK, and it's going to ask us which one. So the one we're going to want to attach it to is AMI 06, so we can make sure that's highlighted, and then press OK. Now what we can see here on our library list is that we now have a new library that's named whatever we just named it. Now we don't have any cells or anything like that yet. So what we're going to actually try and do, now that we have our library made, is that we're going to actually take IV curves for just a simple NMOS. Okay, so we're actually going to look at the IV curves for a simple NMOS. Now, if we start off by making a new cell view, go to File, New, Cell View, double check and make sure that it's on the right library, because you don't want to have to hunt it down later. Make sure that the view is set to schematic, because we're actually going to be making a schematic for this one. But you can see here, there's actually quite a few things that you can make. But the main ones we're concerned with are schematic, layout, and then all the way down here at the bottom somewhere, there should be a symbol. Okay, maybe it's a schematic symbol. Okay, well, we're not concerned about the symbol right now. We're just concerned with schematic. Now, leave it open with schematics L. Now we just need to come up with a cell name for it. So I'm just going to call it AC_EDA1 schematic. So this isn't super descriptive, but because I know that this project is only going to have one schematic, I'm not going to try and use hierarchical designs or anything like that. I'm not going to try and connect multiple cells like op-amps or digital analog converters, anything like that. I'm only concerned with just naming it a schematic. But for example, if I were trying to make like an array of op-amps, I can make op-amp 1, op-amp 2. I could call this one a DAC. I could call it pretty much whatever I need it to be. But for now, I'm just going to call it AC_EDA1 schematic. I'm going to press OK. It's thinking a little bit down here, and then it should be opening a schematic window. Now, this does take some time, and if you're off campus, it's going to take even more time. But once we actually get it up and running, then we will have this schematic editor window here. So schematic editor L, and it's editing the library AC_EDA1, and then the file AC_EDA1 schematic. So this is our empty schematic window. We haven't told it anything that we want to add yet. But if we're taking an IV curve for an NMOS, we are definitely going to need an NMOS somewhere in here. So what you need to make sure is that you have this little yellow square following your pointer around. You can see there's a little bit of latency with mine because, again, there's not going to be a perfect connection to those Linux servers, so there's going to be some latency, and it's going to get worse if you're off campus. But as long as you see this, even if it's a little bit latent, it is still responsive. So what I'm going to do is I'm going to actually create an instance of an NMOS. And what you're going to find is that for schematics, for layouts, for pretty much anything, using hotkeys are going to be your best friend. So hotkeys are going to be keys on your keyboard. That way you don't have to go through and create multiple mouse clicks. So we don't have to come up here, create instance. We can just press the key I. And if we press the key I, this help window is going to open over here. That helps us find things. But if we click over here, what we know is that we want an NMOS, and we can get that from NCSU analog parts. Now, one kind of quirky thing about this that I might want to mention is that sometimes if you just click the down arrow like this, you can see if I just click the down arrow like this, it's not always going to pop open, or it might pop open for a second and then just disappear. That's just because of the latency between us and the server. So if you have those issues, it could be easier if you just press and hold down and then drag to where you need to go. So if I press, hold, and drag to this NCSU analog parts, it'll go ahead and load that up for me. So that's telling me the library that we want to look for. Now the cell we're looking for, I'm going to go ahead and just press it once. You can see these are all the different cells that it has. So this is all the stuff that the NCSU people have made for us. Now what we're looking for is we're actually looking for an NMOS. So if we scroll down here to NMOS, we can see that there's two different types. So there's NMOS and then NMOS 4. Now NMOS, if we actually click it, we can take a look at its symbol. So I'm going to move this out of the way and we can take a look at its symbol in the schematic window. Now, this NMOS only has 3 pins, drain, source, and gate. Now, we should know that in our class, we know that there is actually a 4th pin, and that is the body. So if we want to use that 4th pin, we're going to use NMOS 4. And if we take a look at the symbol here, we can see that it does actually have that body contact. And usually it's going to be better if you just go ahead and use the body contact. That way you can define exactly where you want it connected, and there's no confusion or anything like that. So let's go ahead and just drop this guy right there in the center. Now, we can just hit escape to get out of this window. So if we press escape, it'll close that instance window. And now we can actually start connecting this thing. But before we start connecting it, we want to make sure that we are working with the right component values. So if we take a look down here, we can see that it tells us the width is 1.5 micrometers and the length is 600 nanometers. So this might be good, or it might not be. So if you want to change this, there's 2 ways that you can do it. So I'm going to go ahead and actually delete this so I can show you the first way. And the way that you delete it is you click it. So you just have to click it, you don't have to hold it, and then press the delete key on your keyboard, okay? Now let's say I deleted it and I didn't mean to. I can just press U to undo. There's a second way that you can delete it. You can press delete beforehand and it pops up this cursor with the X on it, and then come over here and click it. Now we need to make sure we escape from this delete tool because it's still open and we don't want to delete other things. So we can press escape and it goes back to our regular cursor. So let's bring it back. Or what we'll do is we'll actually make a new instance here. And it's really easy. We already know it's the NCSU analog parts NMOS 4. You might also be wondering too, why are we using this symbol instead of the schematic if we're in the schematic view? Well, if we take a look at this, we can see that there's actually no schematic cell view. And the reason for that is because we're attaching this to the technology library. All we need is the symbol, right? Because we don't want our schematic view to have all this other weird stuff in it. We just want the symbol, kind of keep it abstracted and help keep us happy and sane. So we're going to be using the symbol here. And whenever this add instance window is up here, so if I escape out, I'll press escape again, press escape again. So if we're just out here and we press I, whenever this instance window pops up, once we go to NMOS 4, we can see down here at the bottom, there's a lot of parameters that we can play with. So let's say, for example, instead of having the width at 1.5 micrometers, we want it to be at 15 micrometers. Well, all we have to do is type in 15 here, press tab, and it'll actually edit it for us. Now, what's cool about this is that it actually gives us all the constraints that we need to keep Cadence happy and to keep the process happy, right? Because not every foundry is going to be able to fabricate things that are super, super tiny, and we want to make sure that it's still within their capabilities. So it tells us down here the minimum width is 1.5 micrometers. So if we try and make our width 1 micrometer, and then press tab, it's just not going to let it happen. It's going to get to the closest thing possible. Same thing, if I try and put 15.05 and we press tab, it's not going to let us get that precise. So it's going to get the closest width that there is. And then we can do the same thing for the length as well. So let's say that we want this to actually be 1 micrometer. So we can't get exactly 1, so it's going to approximate it to 1.05. So that's kind of a cool tool that it uses to help us get as close as we can to the actual value without having to pull our hair out. And then once we get everything kind of looking the way that we want it to, we'll just keep these parameters the same. We can either come back to our schematic window and click it, or we can press hide, and we can still click it wherever we need to. That's just going to hide that last window. So we've got our NMOS put down. So I'm going to escape out of that instance tool. Now, if I'm zoomed all the way out here, it can be kind of a pain to get to where we can see this stuff clearly, right? So one thing that we can actually use is we can use the key F. And if we press the key F, it'll automatically zoom to where we can see everything. So for example, if I'm zoomed in really far on a very complex schematic and I want to look at a top view, I can just press F and it'll zoom all the way back out so that I can see everything and maybe make a little bit better adjustment. So that's just another hotkey to keep in mind. So now we have actually got our NMOS and we can start connecting it. So we know that we're going to have a couple of different connections. And for us, since we're taking an IV curve, that means we also are going to need some sources. So we're going to need an actual voltage or current source to create the energy that we need to actually drive this transistor. Because if we're measuring I or V, we have to have I or a V. So for this one, what we're going to do is we're going to measure the drain current versus the drain source voltage. So what we can actually do to make our lives a little bit easier is we can actually make voltage sources. So we don't have to worry about generating sources or anything like that right now. So if we're just trying to maybe test out a design, we can just press I. Now, instead of working in the NCSU analog parts library, I'm just going to go to analog lib. So that's going to be the default Cadence analog library. And I'm not looking at an NMOS for this one. Oops. I'm not looking at an NMOS for this one. What I want to look at is I want to actually look at a DC voltage source. So if we scroll all the way down, we can see that there is a cell called VDC. VDC right there. And if we take a look actually at some of the parameters, it gives us a DC voltage, AC magnitude, things like that. But we're only interested in DC. So for our DC voltage, I'm going to make this the voltage that is connected to the drain. And our source and body, we're just going to connect to ground. So if this is going to be connected to drain, I'll call this VDS. And if I press tab or click away, it'll automatically fill in the V for us. And then I can come over here back to our schematic window and click it. And it's already filled it in. VDC is equal to VDS. Now we need one more source, so we need a source on our gate. So I'm going to keep the same VDC window open. I'm going to come over here and I'm going to press VGS. I'm going to name this one VGS. Now you want to make sure that you click away or that you tab away because that's how it actually stores those changes. And now we can come and click. And now we've got our VDC equals VGS. I'm going to press escape to get out of this. Now, one thing that I don't like is that I don't like that I've got this so close to our NMOS. So right now it's making it a little bit tougher to read this out. So what I can actually do is I can move this around. And the way that I can do that, you can either click it and press M. So press M and then click it one more time and then drag it. Or you can skip a step and just press M, click on it, and it'll move it around for you. So now I've got it moved in a little bit better area. So now we don't have any connections, so we just have two sources and an NMOS, but nothing is connected anywhere. So what we're going to do is we're going to start wiring things together. So to do that, all we have to do is press W. So W actually opens up the wire key. You can change the width if you'd like to, but I'm just going to keep it default. And what we can do is we can start wiring these connections together. So we want to wire the positive to the gate. We're going to wire the positive of VDS to the drain here. Now, for this bottom pin, we're going to connect pretty much everything else to ground, right? So let's go ahead and make ourselves a nice connection here to this voltage source. We'll add one more over here. Now, one thing that we can do, and this isn't generally a good idea for larger designs, but since we're just starting off with a very basic example, we can do this without having too many issues, is that we need to actually tell it where 0 volts is. Because if it doesn't, if we don't, it's just going to take a guess and it might give us unintuitive results. So if we press I again to add an instance, and we come here to the cell, you can actually delete this and type GND, or you can click on this drop-down menu and find the ground symbol. So ground just gives us a symbol, and that tells Cadence where there is 0 volts. So it's always going to keep this net at 0 volts. Now you may be saying that I forgot to connect this body here, but the reason for that is because I want to show you one way you can check your schematics. And this is actually going to be pretty important. So right now, if you forgot about this body connection, what you might do is you might say, I'm ready to go. So let's go ahead and make sure that we're saving it. And you'll notice that there are two save symbols here. So one just looks like a normal save symbol, and the other one looks like a save with a check mark. So this one here is save that I just clicked. The other one is save and check, or check and save. So what this will do is this will actually check our schematic for any sort of errors or things that we might have missed. And if we click this, it'll tell us that there is a check warning in our schematic. Now it doesn't tell us where exactly it is, But if we close it, we can see that there's a yellow arrow in a box covering that body contact. And that's telling us that we forgot to connect our body. Now, if it was maybe a little bit more abstract or obscure and we didn't know what it was, what we can do is we can actually click on the CIW window. I'm going to make it a little bit larger. And it'll tell us extracting and then warning pin B on instance N0 floating input output. So for this case, this is actually left floating, which is not good because it doesn't know what it's connected to, and we need to make sure that it's connected. So that's one way that you can get an idea of maybe what went wrong whenever you're checking the schematic. And it'll tell you there's one warning and that it's still saved. So let's go ahead and fix this problem. So we'll add one more wire from here, and we're going to connect our body just to ground. Okay? And now we can check and save one more time. And if nothing pops up, we know that we did good. We can also check over here and we can say schematic check complete with no errors. Okay, so now we're making pretty good progress. And now we've got this thing wired up very well. I'm gonna press F just so we can get a little bit better view of it. Now, what we need to do is we need to actually simulate this to see what's going to happen. So the way that you launch the simulator is that you're going to come up here to launch. Oops, let's make sure that I get back to the full view. So that was a pretty good thing. If you just get entirely messed up from your schematic, you can press F and it'll bring you back. But if we come up here, we can press Launch. We can go to ADEL and click ADEL. Bring this window up a little bit further. And you'll notice that it actually changes the schematic window as well. So it changes the schematic window a little bit, but we're just going to work with this simulation window. So if we're working with the simulation window, there's a couple of things we need to do every time that we set this simulation window up the first time. So for every project, every cell, every pretty much simulation state you're going to make, you have to do this setup. So one of the first things we can do is go to Setup, and then we need to tell it the simulator that we're going to use. And the simulator that we're using is going to be the Spectre simulator. And that's all we need to change here. So we just need to change the simulator to Spectre and press OK. And I'll make some changes. The way I always know that I'm in Spectre is that it changes this to 27. So before it was 25, and then it changes the temperature to 27 as a default. So that's one good way of knowing that you're in Spectre. Now, we also need to configure some of the other things, okay? So if we come over to, we need to go to Setup again. Now, we need to tell it what model libraries to use. So if we click on these model libraries, we can see that there's no model files here, so it doesn't know how to model these transistors. So this NMOS that we made here, it doesn't have pretty much any information on how to model it. So what we can do is we can actually click here, and that'll pop up these three dots on the right-hand side. You can click the three dots, and it'll ask us to choose a model file. So right now, this is, again, my Cadence folder. And if you remember that model folder that we copied over from Dr. Lee previously, we can double-click Model, and this will give us all of these different types of model files. So we can see that there is an N type and a P type. And if you are thinking ahead, you might actually say, that's cool, there's an NMOS and a PMOS. And that's exactly what this is for. So this is actually going to be accounting for NMOS, all these different N's here, and the PMOS. Now, the one that we're going to be mainly interested in is NTT, and that stands for N typical typical. So we're actually going to be using this NTT as our model file. So we can double click it, and now it's actually brought in for these models. Now, since we only have an NMOS in this case, we don't need to bring in a PTT file. But if we did have a PMOS, if we're simulating a PMOS instead, or we're simulating N's and P's together, we would actually need to bring in this PTT as well. But for now, we don't need it. So now we've got our simulator set up, and we've got our model files ready to go. So now we can actually get a little bit closer to simulating. Now, if you're in the point of view of the simulator and you look at this circuit, it's not all the way defined. So it might look like it's pretty well defined. We've got everything connected. We saved our schematic and checked it with no errors. But what we can see here is that it doesn't know the voltage at this point, and it only knows that these two are at ground because we haven't told it what VGS is or what VDS is. So that's one thing that we actually have to tell the simulator. So if we actually come over here to design variables, and in this blank area, we come down and right click and click copy from cell view. So that'll actually bring in all of the variables from the cell view and actually create a design variable here for us. So for this first one, let's go ahead and set VDS as 3 volts, and then our VGS as 1.5. So now our VGS is 1.5, our VDS is 3 volts, and now we might think that we're able to run it. So we can come over here, click this green netlist and run button. What we'll see is that it starts doing a whole lot of stuff, but what ends up happening is that we haven't told it what we want it to do, okay? So we haven't told it what exactly we want it to do. So right now, it's just kind of saying, okay, I'm done simulating because you haven't given me any tasks. And if we check the CIW window as well, it started the simulation and then it immediately completes successfully. So it's like if you tell me not to do anything, I'm already done. So what we actually need to do is we need to give it an analysis. So we need to tell it what exactly we want it to do. So to give it an analysis, we can either come up to the analyses here and click choose, or we can use this little button over here. Just use the AC DC transient button here, click on it, and that'll allow us to choose an analysis. Now there's a bunch of different types of these analyses that we can run. Transient is going to be transient versus time. So if you have a time-based voltage source in there. DC is going to be just computing what happens at DC. So it's not going to be doing any sort of AC versus time, anything like that. So that's actually what we're interested in because we're just doing IV curves here. So we're going to start off with a DC simulation. And one thing that you really want to do is you want to hit Save DC Operating Point. So we want to make sure that that is checked because we don't want it to just compute it and then not do anything else. We want it to actually save that information. That way we can view it later in the future if we want to. And then we can just press OK. And now we can see we've actually got this DC analysis set up here. And we want to make sure that's also enabled because if we don't want it to run, we would unclick that box, but we do want it to run, so we can click Enable. So now what we're going to do is we're going to hit Netlist and run one more time. We can see that something's happening in this CIW window, which is a good sign. And we've also got this other window here that we haven't taken a look at yet. So what this other window is this is actually the output from the Spectre simulator. So it's telling us a little bit more information about what's going on. Maybe if there's an error, it might output here, or it might output on the CIW window. But what we can see is that it did converge. So convergence was achieved in 2 iterations. Simulation time was about 7.5 milliseconds, but it took 20 milliseconds for the whole thing. And the total time required, all this other fun stuff, just a lot of information for this DC analysis. And again, we can see simulation completed successfully. Started the simulator, and it's read the simulation data successfully. I'm going to move some of this stuff out of the way so we can come back to this window. Now what we can see is that it didn't really spit out any results for us, but it doesn't mean that it hasn't calculated them. So what we can do is that if we want to view these results, we can actually click on our simulation window. We can click Results. And for these, we could plot them, but it's not going to be very interesting because we've only plotted, or we've only checked this one operation point, so it's just going to be one point on a graph. So what we might want to do is that we might actually want to print the operating points. So maybe we can print the DC node voltages, and it'll open up this window for us here. So it's blank right now, but if we check over here on our CIW window or on our schematic window, we can see down here at the very bottom, it's saying select nets for the VDC output. So it's actually asking us to select the nets that we want to know the operating voltage for. So if we maybe click this point, we know this should be 1.5. If we click it here, it tells us it's 1.5. So this isn't super interesting. It's just computing the voltages that we already know. But if we close this one, come back to our simulation window, we can actually have this printed on the schematic. So we just go to Annotate, and we can click DC node voltages. What we see is that, again, this isn't super interesting. We know that it's 3 volts here, 1.5 volts, and then 0, 0, 0. But this is all well defined. We already defined all of this stuff, so it's not super interesting for us. What we can also do, we can go to Results, Annotate. We can annotate the DC operating points as well. So that tells us some of the current that's flowing through. So this is telling us the current flowing through these voltage sources. And for here, it's telling us the VGS, VDS, and the drain current for this MOSFET. So that's some pretty interesting information, especially as it gets more complex. And then if we want to go back to the way it was before, we can go to Results, Annotate, and then Model Parameters. And that tells us some more information as well, like the gamma. We can also Results, Annotate, and then Component Parameters. And that gets us back to where we were at before. Okay? So now that we've gotten this simulation working at just a single point, We might want to know a little bit more information about this transistor, right? Because we know that the values can often change depending on the VGS or the VDS, things like that, or the drain current. So what we can do is that we can actually check a lot of the variables for this transistor using this results tab here. So I'm going to move some things so we can see both at the same time. Now what we can see, make sure that we can see all of our schematic. So come over here and click F. If we go to results, what we can do is we can hit print once again. And if we go to DC operating points, it's going to bring this window up one more time. And we can see over here on our schematic window, if we come down here, make sure we're clicked on our schematic. This is a little bit touchy, and I haven't figured out what exactly makes this not want to work. So if we close this one more time, we go to results, print, and DC operating points. There we go. So now down here on our schematic, it was actually asking us to select instances for the op output. So down here at our CIW window, it's telling us the same thing, select instances for the op output. So what we can see, if I have this results display window open, if I come to the schematic and I click on our NMOS. So this is actually a way of telling that it didn't work out. So whenever you click on it and it has this little white ring around it, that means it didn't work out the way you wanted it to. So I'm going to hit Control D. Control D is just a way of unselecting everything. And that actually brings me to a pretty good point. Sometimes I feel like I usually think that if I click multiple things, they'll end up getting deselected. But that's not always the case for some libraries. So what ends up happening is you get multiple selected and it's a pain. So I just use Control D to unselect everything. Now, if I close this one more time, or let's see, if I check our CIW, okay, so now we're back on our schematic window, and down here at the bottom it says select instances for the op output. We can click on our NMOS, click on it, and it's still not working. Let's try it one more time. So if we come back to our schematic, select instances for the op output, and click it, we might just have to start completely over. So let's do results again, print, DC operating points, and we'll come to the schematic and we'll click on our NMOS. It is absolutely refusing to work. Perhaps if we go to our CIW window, it'll help us out a little bit more. So select instances for the op output. See, this is not working out for us. Let's see, perhaps there is a different way that we need to do this. Because this is how it was working for me earlier. So if we take a look at this video, or if we take a look at this one more time, make sure it's saying select instances for the op output. That is just not working. Let's try DC node voltages again, make sure that that's working. So if we click on this node here, it's still just not working. So let's make sure that we're escaped out of everything here. Let's click on our schematic and escape, 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 just to make sure we're out of everything. And we'll try this from the very beginning one more time. So if we hit print, DC operating point, and then come and click on our instance here. Now we've got everything working. So I guess maybe there was some tool open in the background on the schematic window that was causing it to select instead of doing what I actually wanted it to do. So maybe coming to the schematic and pressing escape multiple times is how you can get it out of there. So now we can see up at the top, it's checking the operation for N0. And we can actually see quite a few things about this. So if we scroll down, we can see things like our VGS, our VGD, VGB, and we can also see things like our VDSAT here. So our VDSAT, VDSS, and then we can see our VTH as well. So we can actually use this stuff to see a little bit more about what exactly is happening in this MOSFET, because we know that some of these values are very important for our calculations. If we scroll up, we should be able to see something like our GM, our GMB, things like that here. We can also see different capacitance values and things like that. So there's a B effective, beta effective, all sorts of different things to do with this NMOS that could be important. So if you need to calculate the operation point for a MOSFET at any point, or at a certain DC operating point, this will be a good way of actually figuring that out. We've also got our R on and things like that. Now, I do believe this is part of your homework, so this is going to be something that you need to do. And if you do have any issues getting this operating point, just let me know and I can help you try and figure it out. Okay? So now that we've got our DC operating point, we actually want to see how this DC operating point changes if we maybe change one of these values. So for part of the homework, we're going to be simulating the ID versus the VD, or the ID versus VDS. Yes, so we're going to be simulating IDS versus VDS and sweeping VDS from a certain value. So the way that we can do that, if we double click on this DC analysis, you might have noticed earlier that there is a sweep variable here. So you can sweep things like temperature if you wanted to, and it pops up this sweep window, but we're going to be sweeping a design variable. And it's going to ask us for our variable name. You could type it out, but I think it's easier if you go select design variable and then click the one that you want to. That way you don't accidentally mistype or anything like that and wonder why it's not working. So the sweep type, it's just going to ask us for a start and stop value. So let's go from 0 to 5 volts. And then sweep type, we can do automatic, linear, logarithmic, whatever you need, but I'm just going to leave it as automatic. You can also add specific points if you wanted to, change it from center to span, but this is going to work well for us. So if we press OK, we can see that this argument changed a little bit. So we're sweeping from 0 to 5, it's an automatic sweep and a start-stop sweep. Now this time, if we actually run it, what we'll see is that over here on our schematic window, everything has stayed pretty much the same. So everything here has stayed pretty much the same, and that's because the annotations that go on the schematic are based on these values in our simulation window. So these design variables that we gave it in the very beginning. That's why VDS is 3 and VGS is 1.5. But not all the results are that way. So if we click on results again, what we're actually going to be doing is we're actually going to be plotting the current versus, versus the different values. So we can go to direct plot, main form, and it's going to ask us maybe if the license isn't available, just click yes, and it should eventually open the window once it finds the correct license. And this is going to be our visualization and analysis window. Get everything resized so we can see everything. Now it should pop up, yes, this direct plot form. So we are going to be looking at DC, and the function, the thing that's going to be going on the y-axis in this case is actually going to be a current. So we're going to be measuring a current. Now down here, we actually do want to add it to an output, right? Because we don't want to have to go through this same process every time we press simulate after doing something like changing the gate source voltage. So we're going to go ahead and add it to the outputs, and that'll just automatically cause it to add it to the outputs and display the graph. Now down here it's saying select instance terminal on the schematic. So if we come to the schematic, we can see that I'll go ahead and just press escape a couple. Oops, that's not what I need to do. Well, I guess we can repeat it one more time. So we're going to again go results, direct plot, main form, let it load up. Then once again, once everything gets loaded up, we're looking for a current, add it to the output, come to our schematic. Now, it's asking us to select an instance terminal. So to measure the drain current, we can click this value here. So if I click that terminal, we can see that it's actually plotting over here on this screen. Now the current is negative because this is actually measuring the current going into this terminal. And the current going into this terminal is actually negative because we know that there's current leaving this terminal because this is an NMOS, current is flowing down. So it must be leaving this terminal here. So if we want to get this right side up, what we can do is we can actually go back to this direct plot form that we had previously. We can click on this bottom terminal instead. And now we've got the positive value of it. So it's measuring the current going in, which actually translates to the drain current here. Now, one other thing that we could try and do is we could try and click the drain terminal on the MOSFET. Now, whenever we click that drain terminal, you can see it doesn't give us that little circle. And if we come over to our direct plot window, it tells us that N0 drain is not a kept output. So this is actually something that's going to be pretty important to work with because we oftentimes do want to know maybe the current inside an individual transistor and not what is just happening at the source. So let's go ahead and press OK here. Now, on this visualization window, since we already have the current, I want to go ahead and get rid of this value here, so this red curve. So what I can do is I can come over here to the left, right click it, and then we can come down to delete, and that'll go ahead and get rid of it. Now another thing that we need to do, because we know that that value isn't exactly good for us, it's going to be negative, which is not what we want, we can come back to our simulation window and notice that there's a couple of outputs added here. So whenever we have add to output, it's actually adding to this list of things to give us, and one of them is this value here, that that current coming into the plus terminal of V0, which we know this is negative and it's wrong. So if we right click here, we can just simply hit delete and it'll get rid of it for us. So now we're only left with this V0 minus, and if we run this one more time on our visualization and analysis window, we should still have that same one. And it's changed colors now, so it got reassigned to the red color. Now it's also saving what's happening at that terminal. So what we can do instead, so let's assume, I want to show you guys one more way because this will be important later on if you have maybe more complex designs, is I want to show you how to actually add the information for this NMOS into the kept outputs. So I'm going to go ahead and close this one, and I'm actually going to just delete all of this stuff here. So if I right click here, delete, and that's going to get rid of all this stuff here. Okay, so now we're just back to the way we were before. And if we tried to do direct plot main form on this drain terminal here for the current, it wouldn't work. And I'll do that one more time just to verify. So results, direct plot, main form. Gonna have to wait for it to load up again. But once it gets loaded up, it should tell us that same thing. So if we're measuring the current, and we try and click this terminal here, and we can see nothing's getting added to our window here, and it's saying N0D is not a kept output. So what we can do is that if we come back to our simulation window here, our Spectre window, if we click on outputs, we can actually click setup, and then we can get an expression from design. So what we want to do is we want to get from design here, that way we don't have to guess what the expression is. And if we click from design and come over to our schematic window, it should give us an option. Oh yeah, so we can see down here at the bottom, selecting outputs to be plotted. So if we click on this one right here, you see it actually grabs all four of those different values here. So maybe if I don't want all four of them, maybe if I don't want the body or anything like that, I can delete that expression. Maybe I don't want the gate because I know it's 0, I can delete that one as well. So now we just have drain and source. Now I know I don't want source, so I'm going to go ahead and delete it as well. But now we can see that it's added to our outputs here, and it's already selected to plot. And if we run this one more time, it's saving it, and it's asking us to open the visualization window, which is a good sign. And what we can see is that we have now got this nice drain current curve here. So we got a nice drain current curve, and we don't have to do anything weird like click here at the voltage source. Now, this is a little bit small, so if we want to increase the size, we can just right-click on the curve. So if we right-click on the curve, we can change the color, and you can also change the type, the style, and the width. So the style, I want it to be just a solid line. And the width, see, it's a little bit cut off here, so maybe if I move down over here, the width, I want it to be, go ahead and just make it thick. Now it's a little bit easier for me to see. Now, one bad thing about this is that whenever you resimulate, it undoes all of that work you did to change the style and the width. So this is probably something you're going to want to do as you're taking pictures or screenshots of this output, not something you're going to want to do every single time. Now, this is a nice IV curve, but it's only at this one specific gate source voltage. So we might also want to see how this changes for a variety of gate source voltages. So what we can do is that we can actually do what's called a parametric sweep. So if we do a parametric sweep, that's actually going to allow us to sweep a second variable at the same time. Now you're not going to want to do a super fine sweep, like you're not going to want to do it in millivolt steps from 0 to 5 volts, because that would just be a whole lot of computation and take way too long of a time. Excuse me. But what we can do is we can give it maybe 4 or 5 values for it to plot. Okay, so what we can do, we can come up to Tools and then click Parametric Analysis. So we can come to parametric analysis, and then here we can click Add Variable. If we click, it'll open up this drop-down window. It automatically includes, see, this is one of those cases where you have to hold it down. It automatically includes the temperature, but right now we are going to sweep the gate source voltage. So this is not what's going to be on the x-axis. It's just going to run the simulation multiple times for different values of VGS. So if we have our VGS, we can do a couple of different ways. So we can maybe tell it the step mode. So we can say that we want linear steps, auto steps, pretty much whatever we want. We can, instead of doing from to, we can do a center span or a center span percent. But what we're going to do is we are going to do from, let's just go ahead and make this from 0.5 volts, something that we know is below the threshold voltage. And we'll do to 1.5 volts. Now the total steps, let's just go ahead and make this 5 steps. And these are just numbers that I'm throwing out. We'll keep the step mode at auto for now, but if you needed to, you could make that linear or logarithmic, whatever you needed. Now, if we just come back down to the simulation window and click this green arrow, it's going to run this exact same simulation here. And if we wanted to do the parametric analysis, we actually have to have the parametric window open, click this green arrow, and then we'll see a little progress bar down here at the bottom. 60, 80, and then 100. Now we can come back to our plotting window. And what we can see is that now we've got 1, 2, 3, 4, 5 curves. It might be hard to see the difference between these two down here at the bottom because our VGS is still pretty low. But we do have about 5 curves going all the way from 0.5 volts to 1.5 volts. Now, you could also go through and change these line thicknesses and things like that. Or you can click on all of these here. Maybe you can change the trace group properties. You can work with them just a little bit easier. But one thing you can do is, like right now, we can't really see these two down here at the bottom. So what we can do is we can right click anywhere on the graph and then do split current strip and trace. And what that does is that actually makes an individual graph for each and every single one of these. And it tells you, so like down here at the bottom, whenever we're at a VGS of 0.5, maximum we get is about 3.5 nanoamps. Here, VGS of 0.75, 1.4 microamps, then 35, 140, and then a lot larger value here. So that maybe gives you a little bit more resolution on how to see all of these. And then if you want to get them all back on the same one, right click again, combine all analog traces, and now they're all back on the same trace, or on the same graph. So this is going to be our VGS, or our VDS for different values of VGS. And then you can also run another simulation. In this case, you would want to change this to maybe where you're sweeping your VGS instead, so you can see your IDS versus VGS. And let's go ahead and do that as well. So we'll sweep this one. Instead of VDS, we'll do VGS. And on our parametric sweep, we will change, not VGS, because that's already our x-axis. Let's change VDS, and we'll go from 0.5, and we'll do to 5 this time. And we'll just do the same, actually, let's just make it 0. 0 to 5, and we'll take 5 steps. Just for me, I'm going to make it 6 instead. That way it's even 1 volt steps. Now we can run this one more time. Okay, it's going to open up our visualization window. And now we can see this VGS versus, this ID versus VGS curve. So it's still taking the drain current of N0. And now we're seeing that for these different values of the drain current, we are actually getting way different current values, right? And again, if we wanted to maybe see these with more detail, we can split the current strip, trace, and now we can see all of them in just a little bit more detail, okay? So this is a pretty good way of seeing, doing the parametric analysis and getting a feel for how these different transistors are working. Let's go ahead and combine all these analog traces again. And I'm going to look through and make sure that there's nothing else that we need to keep hitting. So maybe, so one of the things that we can do is that we can come back and we can maybe see what happens if we add a voltage source here. So maybe this is something that you could do in your spare time. But if you for example, change the schematic, come back, and even if I make the exact same changes to where it's the exact same way that it was before, we need to make sure we're hitting this save and check button every time. So if we don't save it, it's going to get really grumpy. If we don't save and check, it's going to get really grumpy with us. And if I try and run this simulation again, what's going to end up happening is that nothing happens. So we're not seeing any major thing happening here or on our CIW window. And if we check our CIW window for some information, what we'll see is that netlist generation failed because of the errors above. Netlist might not have been generated, so it's unsuccessful down here at the bottom. And if we look up above, we can see an error. The cell view schematic has been modified since the last extraction. Verify that the schematic is correct and run check and save to correct this error. So that's a pretty good way of figuring out what's wrong. He's using the CIW window. So if we hit check and save one more time and then try and run the simulation, we'll get a lot better values. Great, now we can see that this does look a little bit more like that VGS versus VTH. Okay, so I think that I've covered just about everything that we need to for this first tutorial to get you familiar with Cadence. But if you have any questions, please feel free to let me know. And if you want to maybe start working ahead, experimenting with different things, that's definitely a good thing to think about and would definitely help you out. So like I said, if you do have any questions, please feel free to email me or get in touch with me any way possible, and I'll do my best to help you guys out. So thank you guys for watching. So one last thing that I wanted to add, actually, forgot about this until after we stopped the recording. But one thing that I wanted to add is that if you have an image like this, for example, one thing you could do is you could just take a screenshot from your Windows machine. But this dark background is not exactly good for printing or anything like that. So one thing you can do that makes it really easy is you can just press File and then Save Image. And then you can actually export this as an image. Now, one thing that's pretty important here is it says replace the background color with white in this case. You can also change the resolution, the width, height, things like that. You can also click maintain aspect ratio to keep it the same size as it is on your screen. But for now, I'm just going to override it as this currently existing one. And then if we pop back over to our MOBA extern, what we'll see is that now I've got this file up in here. So MOBA extern has a pretty cool way of actually seeing this SSH browser here. It actually shows you the file system that you're currently in. So it might start off, if you don't have this follow terminal folder on, it might actually start off all the way up here. But if you just double click on your, or double click on the file or the directory wherever your image is stored, and then double click on the bitmap file that we just saved, it'll take a little while to open it because it is a little bit larger file. But it opens it, and then it's this nice white background, and it makes it look a whole lot better, and it's a lot easier to see maybe some of these strips, especially if you make them those lines a little bit thicker or solid lines. So that's just one last thing that I wanted to add because that could be pretty important. If you're handier though, you could also find it easier to just take a screenshot and invert the colors, but that's entirely up to you. So once again, thank you guys for watching, and if you do have any questions, please let me know.